Hello class, welcome once again to our uh, lecture for today. So this is a continuation of our video lesson series. This is the third part of the topic electric field and electric forces. Okay, so we have here another problem. So point charges Q1 and Q2 of positive 12 nanocoulomb and negative 12 nanocoulomb respectively are placed 0.10 meter apart. This combination of two charges with equal magnitude and opposite sign is called an electric dipole. So compute the electric field caused by Q1, the field caused by Q2, and the total field at point A, B at point B, and C at point C. So meaning at this point, so we are asked to compute the electric field caused by Q1, okay, caused by Q1 and caused by Q2. So we also have to calculate the total field. So total field at point A. So where is this point A? So this point. So at this point, and also at point B. So meaning at this point, and point C at this point. All right. So here's the solution, class. So at point A, so at this point A here. So we have again we use this formula now for electric field. So for E1, now let's consider it as E1. So at this point A here, so we have 1 over 4 pi A epsilon sub 0. Okay, so this is our K actually. Then multiplied by Q1 divided by R squared. But we know that this part already, uh, this has been calculated already, class. Right, so this is just our K, which is after calculating, substituting the value of A sub 0. So we have a constant for this one, multiplied by 4. 4 is constant, pi is constant, so we get this result. So now we just take the value for the Q1, absolute value of Q1, which is 12, no, given the problem that is 12 nanocoulomb. Okay, and then the distance equal to 0.6, meaning the distance from discharge, from discharge from Q1. So this is this distance. So that is 0.06. So we use meter here, class. So 0.06 meter, or that is 6 centimeters. But in our calculation, since the unit of the charge is in terms of Newton meter, so we need to convert this into meter, which is equal to 0.06 meter. Then you square that one, so you get this result. Okay, so we have to be consistent with the unit. We are given here in terms of centimeters, but since the unit of coulomb is in terms of meter squared, so we have to make it in meter also. Okay, now for E2. So E2 meaning here, the electric field due to this charge. So again, they have the same charge, absolute value of that. So positive, so same value for K, the constant. Okay, then the distance now is here, meaning from point A. So the distance of charge Q2, okay, that is 4 centimeters, or equal to 0.04 meter. You square that one, so multiplying with this, so we get this. So that's our A sub 2. Now that is electric field due to charge Q2. So now let's calculate for the horizontal component, no? Or the x component of this electric field. So for E1, that is caused by this charge Q1. So we have 3 times 10 to the 4th coulomb. So that is the x component, because that is horizontal, no? So this in x component, so that exactly the horizontal component of this electric field. But E sub 1 y is equal to 0 because they have no vertical component. All right. So this one has no vertical component. So a sub 1 y equal to 0, and e sub 2 x is equal to this one, and the vertical component is also equal to 0. Okay. Now to get the resultant of the electric field at this point A, so you just sum up. Okay, you just sum up. We have this. Okay, you sum this up. So we got here uh, this one equal to 9 point. Sorry, this is to sum this up. So when you add this one, 3.6, so that is 9 point something, no? 9.8 times 10 to the 4 Newton per coulomb. So this is our this indicates our J component, meaning the X component. But we supposed to have a J component here, but this is 0. So this is our resultant, no? Electric field on the x-axis. Okay, so that is on at point A. Now we're still at point A. So how about at point B? So at point B, so now we'll consider this part here. All right. So at point B, so we have E1. So this time, because this is caused by this charge Q1. All right. So same value here for this constant. Okay. So same value as in the previous slide. We get this one, then same charge, but now the distance is, so from Q1, this is only 4 centimeter, or that is 0.04 meter. You square that one, so you get this 6.8 times 10 to the 4 Newton per coulomb. Okay, now with reference to this charge Q2, so the total distance that we're going to use is this one. Okay, so this is now the total distance that we're going to use. Okay, and this is 10, this is 14 centimeters. 14 cm. All right, so here we have same constant. Okay, this one, then same charge here because they have just the same charge, and then this time the distance is 14 centimeter is just 0.14 or 0.140 meter. Okay, so that is the total distance from this charge to this point B. Okay, so same thing, we calculate the horizontal component. So this is the horizontal component, and again the vertical component or the y component is 0, and so do we this one. Okay, so we have and then we have the point B. So subscript B means we are referring at this point. So again, the resultant is you just add all the components, horizontal components as well as the vertical components, but the vertical components is equal to 0. Okay, so that's why we have the electric field at this point due to these two charges is equal to the negative. So this is negative class because it's, you see, it's going to the left. All right, so going to the left, meaning after we calculate, because this is E1 sub x, so we get this negative because it's in this direction, and this one is positive going to the right. So when you sum up the two, so we get this result. Okay, that is negative 6.2 times 10 to the 4 Newton per coulomb. This is the I means the horizontal component. The vertical component is equal to 0, so no need to write the part here that's supposed to have or supposed to contain the J component. Okay, so this is the answer for part B. No, this is at point B. So a while ago we have this one. This is for at point A. Okay, now we go to the third point. So at third point, at point C, meaning we'll consider it this point here. So at point C, so again, same calculation class. So take note that since this is symmetric, right, they are symmetric, this is an isosceles triangle. Okay, so an indication of an isosceles, they have the same length for this side and also this side. Okay, so this is symmetrical. So this is an isosceles triangle. So we can say that A1, so whatever value we can get for E1 here, so that is also for this part A2. So they're just equal. So the calculation is same, use the same constant, then same charge. So the distance from Q1 to this point C is equal to point, or that is 13 centimeters or 0.13 meters. So we got here E1 equal to E2 equal to 6.39 times 10 to the 3 Newton per coulomb. Okay, then again, solving for the horizontal component. So, but this time class, we have already an angle, right? It involves an angle. So we have here an angle here to help us solve for the horizontal component. So we have to make use of this angle alpha. So since this is isosceles, so this alpha here, this angle here is alpha, this angle is alpha. So okay, you can use either this alpha or that alpha. Anyway, they're just the same. Okay, and this angle here is just the same as the angle here. This is also alpha, or this one. So if this is alpha here, so it means this is also alpha. You see, this is also alpha. And if this is alpha, this is also alpha here. Okay, so this is also alpha here. The angle here is alpha. All right, so substituting to solve for this angle, you can have you can use the cosine. No, cosine is adjacent over hypotenuse. So adjacent. Okay, so we have to make use of half of this triangle. So you divide this triangle into two. Okay, so you just so it means that this one from the half of this, because this is 10, so half of this is just 5. No, this is 5 centimeter. Okay, 5 centimeter. So when you say cosine, so cosine is adjacent over hypotenuse, so that's why our adjacent here is 5. Okay, because our E1 sub x or E1 sub E sub 1x equal to E sub 2x is equivalent to E1 cosine of alpha. So our cosine of alpha here is adjacent over hypotenuse, that is 5 over 13. So we have it here. So therefore, our E sub 1x equal to E sub 2x is equal to 2.46 times 10 to the 3 Newton per coulomb. All right. So to solve for the resultant, no, uh, resultant of the EC, no, the EC, the resultant of the resultant of this electric field here at this point. So just the summation of the component that is due to Q1, the charge Q1, and also the due to Q2. And since they are this is an isosceles, so this is symmetric, right? So whatever is the value for electric field here, the horizontal component of this electric field, this one that is caused by this is just the same as this one. So therefore, you just take this and multiply it by 2, because E1, E sub 1x and E sub 2x they're just equal. Okay, so you just multiply any of them and you get the result. Then again, for the vertical component, so these are just 0. So the electric field at this point C is equal to this one. And you have I here to indicate that this is the horizontal component of the electric field, only because the vertical component of it is equal to 0. Okay, so I hope it's clear with your class, and that's all for this example, and hope to see you again in the, I think, the last video for this topic, part 4. Okay, so thank you very much and see you in the next video. Bye.